We're going to continue our talk today on logarithms. We're going to start by talking about two very special kinds of logs. You may have seen them both yesterday a little bit, but we're going to talk more specifically about them now. That's the common log and the natural log, and these are the only two your calculator actually has buttons for. There are ways to do other logs, but we'll talk about that another time. The first is the common log. So the common log is just log base 10. Often they don't actually write the base since it's called the common log. Anytime you see a log without a base, one that's written log, if there's no base written, it's understood to be log base 10, so the common log. The other one is the natural log. And this is actually log base e. Remember, e is in fact a number. It's 2.71 something. It does represent a number. And it's often written as just ln of x. Log base e is the same thing as the natural log of x. So it's important to remember that the natural log is the same thing as log base e. The base for natural log is e. Now that we've talked about the natural log, one thing that we didn't get to yesterday was the inverse properties for natural log. Just a quick reminder of what we saw yesterday. If we had log base 7 of 7 to the x, that just equals x. Basically the log base 7 and then this 7 cancel each other out and it just leaves the x. Or if you have 7 raised to the log base 7 of x, they also cancel each other out there and you're just left with x. So that's just a reminder of what we saw yesterday. So that's what we saw yesterday. So today we're going to look at the inverse properties for natural log. So for example, if you see the natural log of e raised to the 5th, your answer is just 5. Now again, I know it's not written there that we have an e as our base, but you should know because it's the natural log that your base is e. It's understood. If you look back up here, you can see those two things are equal. Log base e and natural log, same thing. So you assume that that natural log has a base of e, which cancels out with that e, leaving just the 5. Okay, same thing if you have e raised to the natural log of something. The e and the natural log cancel each other out. So this would just leave us with x. Now that's going to be important later on when we start solving functions that have logs in them and things like that, when we have to solve equations with them. So it's important to remember that e and natural log cancel each other out. The next thing we're going to look at is the graphs of logarithms. First thing I want to make sure is clear is that logarithms are inverses of exponentials. Remember, we started this unit with exponential functions. I'm going to show you just general graphs of each one so you can remember what they look like and see what they look like. Here's an exponential function. And then here is a logarithm. So hopefully you can see why they're inverses. Inverses are actually functions that are basically reflected across each other along that dotted line I just drew. That's the line y equals x. You don't have to remember that fact right now, but that's why they're inverses. So exponential and logarithms are inverses. Also, if you remember, I told you if it's just a basic parent function exponential, it hits the point 0, 1. So hopefully, then you can figure out that that means the logarithm must hit the point 1, 0. Because they are inverses of each other, so their x's and their y's are flipped. That's why it flips over the line y equals x, because x and y gets flipped. We also talked with exponentials about translations or transformations or things where that moved or shifted. So we're going to talk about that here as well. It's basically the same, but I want to make sure it's clear. So first of all, let's say we have log, we'll use common log for this. log of x plus c. Notice the c is being added only to the x. That means we're dealing with left and right, because the x-axis is the horizontal axis, so x has to do with left and right. If you add c, that means you are going left c units. In other words, if it was x plus 3, that means you're going left 3 units, or x plus 5, you're going left 5 units. So then the opposite, if you do x minus c, means you're going right c units. So that's what happens if you add or subtract a number just to the x. Now if you do it to the entire function, okay, notice right here there's no parentheses, so you assume that c is not inside the log. It's being added to the whole thing. And if that happens, then you're moving up c units. And then log of x minus c would move down c units. Now just so you know, I'm using common log, like I said, but this works for any logarithm at all. It could be natural log, it could be log base 7, log base 9, it doesn't matter. This holds true for all of those. Okay, now if I put a negative in front of the whole thing, that's going to be a vertical reflection. Means it flips it upside down, basically. Because you're doing negative to the whole thing, so that's a negative to the y, so that's why it's an up and down flip. If you have log of negative x, it's a horizontal one. Horizontal reflection. So that means it flips it left and right. So I'll just draw some quick pictures of this. This one would look like this. Something close to that. And then log of negative x would look like this. So you can see it flips it up and down for the log of negative x, flips it left and right for this one. Now let's talk about the domain and the range of logarithms. We'll start by just considering just normal log of x, natural log of x. If you look at the domain, remember domain is the x values, it's how far left and right you go. The domain is going to start at 0. It doesn't touch 0, so we're going to put a parenthesis instead of a bracket. But it starts at 0 and then goes all the way to infinity. Remember, that's how far left and right you go. It's your x values. Your range is your y values. Well, this graph goes all the way down to negative infinity and eventually goes all the way up to positive infinity. Log is very slow. It doesn't go up very quickly, but it does continue to go on up forever and ever. And this domain and range is true for any log. This would be true for log of x, which is common log, or natural log, or log base 7, log base 10, log base 3, any of them. This would be true. Now if you start shifting things, like when we were looking at transformations, that can change. But as far as just the basic parent function, any of the logs, this is true. So if you notice, the domain has to be positive numbers. So you cannot take the log of negative numbers or 0. So only positive numbers work. I'll just write that. Only positive numbers work. That means no negatives, no zeros. So sometimes you may be asked to find what the domain of a log is. So let's talk about how we would find that. So for the first example, let's do log base 4 of x plus 3. So this is actually pretty straightforward. All you need to do is figure out how to make sure that all the x's that you plug in give you a positive result. In other words, what's inside has to always stay positive. Another way to say that is x plus 3 has to be greater than 0. Has to be, because we cannot do the log of a negative or of 0. So we just solve for x, subtract 3 from both sides, and we get x is greater than negative 3. So that's our domain right there. So notice, you can plug in negative numbers. If we plugged in negative 2, for example, that would be fine, because you have to add 3 first, and so you would get a positive number. So it's not that you can't necessarily plug in 0 or plug in a negative number, it's just that your result on the inside cannot be negative or 0. And that's an important distinction. So your domain would be x is greater than negative 3. Just so you know, one other way to write that would be negative 3 to infinity. That would be another way to write it. You can write it either one, both are correct, but it's important that you know that those are equivalent to each other. Okay, next example. Let's do log base 4 of x minus 5. Let's change the base. Let's do log base 3 of x minus 5. Because it doesn't matter. Same thing either way. We've got to make sure that what's on the inside is greater than 0. X minus 5 is greater than 0. Just add 5 to both sides. We get x is greater than 5. So that is our domain. That simple. You could also write it in an interval form, which would be from 5 to infinity. If you're having trouble seeing how I'm converting from here to here, just think about a number line. We know our division or our point of divide is at 5, and that we can use all of them greater than 5. So I would put an open circle here and do everything greater than 5. So if you think about it, what I'm highlighting is everything bigger than 5, so that would be 5 all the way up to infinity. Okay, let's keep going. Let's try one with a natural log, because it works the same way. Let's do the natural log of 3 minus x. Again, what's inside has to be greater than 0. So I'm going to subtract 3 from both sides and divide both sides by negative 1. Here's one place you need to be very careful. Remember that if you divide or multiply by negative 1, you have to flip over the inequality sign. So it becomes x is less than 3, or negative infinity to 3. Either one of those would be a correct answer for the domain. Again, if you think about your number line, here's 3, we're going to do everything less than 3. So that's why it goes negative infinity to 3 for that one. Okay, one last example. Say we have the natural log of x minus 2 squared. Okay, x minus 2 squared has to be greater than 0. Well, this one you kind of have to reason through a little bit. X minus 2 squared is always going to be positive, because squaring something is always going to be positive, except when you're equal to 0. So what you need to look out for is what you would plug in for x that would make this 0. Anything else you plug in is going to be fine, because the square is going to make it positive. But you can't let it be 0. So this domain is actually x does not equal 2, because you can't let x equal 0. So you could write it that way, or in interval notation, it would be written that way with 2 intervals. So either one of those is a correct way to write the domain. You could say all real numbers except 2, or x does not equal 2, or that interval right there. Okay, we're almost finished. I just want to show you one example of a word problem with natural log in it, just so you are familiar with it. So here we go. Sorry, I'm not sure why it's highlighting all that for you, but oh well. We have that w equals 0.35 natural log of p, there it goes, plus 2.74, and it says that this models the average walking speed, w, this is actually in feet per minute, or feet per second, for a resident in a city of p thousand people. That just means p is in thousands. So New York City has 7,323,000 people, so that's really 7.3 million people. Find the average walking speed. This is really straightforward. This is the number of people, that's population. So we're going to get 0.35 natural log of 7323 plus 2.74. And if you plug this in your calculator, your natural log button is on the far left, right next to the 4 basically. You should get about 5.85. So in New York City, according to this equation, the average person walks at a speed of about 5.85 feet per second. Alright, that's it. I'm just going to copy and paste the homework for you. And I'll wish you good luck. Make sure you practice these. Please note that on this section 49 through 52 right here, I don't want you to follow their directions. I just want you to describe the transformation.